triple integrals in cylindrical and spherical coordinates. First, we start with triple integrals and cylindrical coordinates. You want to recall from the polar coordinate system with x and y that x is equal to r cosine theta and y is equal to r sine theta. And then in the space, we pick up z, so z is equal to z. We represent a triple integral over a solid Q of a function with respect to the volume. Here we have the integral from theta sub 1 to theta sub 2, which denote the boundaries for theta with the upper and lower limits. And then g sub 1 of theta, the integral there, the lower limit, and the upper limit, g sub 2 of theta, which would be the boundaries for the radius. And then the integral on the inside here, h sub 1 of here, this represents x and y, r cosine theta, which is x, and r sine theta, which is y, to the upper limit of h sub 2 with respect to r cosine theta and r sine theta. The function is f of x, y, z, where x is r cosine theta, y is r sine theta, and z is z, with the factor from, you recall from before, dealing with the double integral, converting to polar coordinates, we have the factor of r. Since this is in the space, we have dz, dr, d theta. Now the order can be reversed in whatever way to your advantage. So it could be dr, dz, d theta, or dz, or d theta, dz, dr, d theta, dr, dz. So the combinations there that you can use, a few of those, in terms of reordering the order of integration. Now I want to look at the setup for triple integrals in spherical coordinates. Where here x is, you recall back in chapter 11.6, where we talked about 11.6, 11.7, we talked about the introduction of cylindrical coordinates and spherical coordinates. And so here we have x equal to rho sine phi cosine theta, y equal to rho sine phi sine theta, z equal to rho cosine phi. And if you recall that what we had was oh, I need some more. Now I got to try to get all these variables in there. Instead of drawing it bigger. So here, this side is x, this is y, the angle theta, I need this to be bigger. This is z, this is rho in there. Oh, I can't see any of that. What did I get myself into? think this is better. Yay! I used to like blue, but the black is looking better. Here's the angle theta. I guess I better draw theta first. This side here is x. This is y. This is r. This is z. This is rho. And this angle in here is phi. So phi is there. This is z. This is rho. We form a parallelogram, so this is r up there as well. Now, if you extract this right triangle with phi in it, let's see if we can pull that out. We have phi. Here we have z. This is rho. And this is r. And so if that be the case, then notice that the cosine of phi is equal to z over rho. This implies that z is equal to rho cosine phi. We get that. Now, what about sine? Sine phi is equal to r divided by rho. So that implies that r is equal to rho sine phi. Now, we know that from cylindrical coordinates, x is equal to r cosine theta. But if r is equal to rho sine phi, and then times cosine theta, we build this one. And likewise, y is equal to r sine theta, but r is rho sine phi, and then times sine theta. So it all makes sense. And so to build the triple integral in spherical coordinates, we have a triple integral over the solid Q of the function to evaluate with respect to the change in the volume. And so here we have three integrals. This integral here gives the boundary for theta, where theta is bounded between theta sub 1 and theta sub 2. The next integral gives the boundary for phi, where phi is bounded between phi sub 1 and phi sub 2. And then this third integral gives the boundary limits for rho. Rho is bounded from rho sub 1 to rho sub 2. It's the function. We're here. This represents x. This represents y. This represents z. And we have the correspondence there that we just got through showing. There's a factor into the formula, which is actually the volume of a cube when you look at the Riemann sum for the triple integral, looking at the summation and the limit and summation formula. So that factor that you get for a small cube to calculate its volume is rho squared sine phi. So we have that factor in there in computing here the overall volume, if you will, for the solid. So you have to inject this, just like how you injected R for the cylindrical coordinates. So I think with that we can work some problems. Let's take the first one. Here, just straightforward and integrate. I'm going to integrate first with respect to R, then with theta, and then after that, lastly, with z. So we have the integral from -1 to 5, the integral from 0 to the power over 2. So they've already done the work for us. They just want you to, they've done the work to set up the triple integral. They want us now just to compute the triple integral. So we integrate with respect to R first. So this is 1/2 R squared, and R goes from 0 to 3. Then we have cosine theta d theta dz. So plugging in R to be 3, we get 9/2. We can just put that in the front, times the integral from -1 to 5, the integral from 0 to power over 2. This is cosine theta d theta dz. Integrating with respect to theta, we have 9/2 on the outside, the integral from -1 to 5. This gives us sine theta, where sine is evaluated from 0 to power over 2, and then this is dz. Well, sine of power over 2 is 1, minus sine of 0 is 0, so all we have there is just 1 times that 9/2. This is the integral from -1 to 5 dz. So this gives us 9/2 z, and z is evaluated from -1 to 5. Just could have said 9/2 times the 6. 5 minus a -1. So 9 times 6 all over 2. So let's look further. Look at the next problem. It's not 9 times 2, 9 times 3. 2's cancelled, 6 divided by 2 is 3. 9 times 3, excuse me, 27. Oh, it's getting late. It's almost 9 p.m. and I'm still here. So that's good. So this is 9 times 3. Sorry. Oh, okay, so now we integrate with respect to z. So we have the integral from 0 to power over 2, the integral from 0 to 2 cosine squared theta. Integrating with respect to z, this is 9 sine theta here times z. Integrate there with respect to z. Evaluate the z from 0 to 4 minus r squared. So this is dr d theta. It's easy because there is no z there, so the integral of dz is just z. So this is 0 to power over 2. This is the integral from 0 to 2 cosine squared theta. And we evaluate the z at 4 minus r squared, so that gives us r times 4 minus r squared. Evaluate z at 0, everything goes out. This is times sine theta. This is dr d theta. Let's simplify this. This is the integral from 0 to power over 2, the integral from 0 to 2 cosine squared theta. This is 4r minus r to the third times sine theta dr d theta. So we integrate with respect to r is dr that comes next. This is the integral from 0 to pi over 2. This becomes 4r squared divided by 2, so that's 2r squared minus r to the 4th over 4. We evaluate these terms from 0 to 2 cosine square theta. Then here we have sine theta d theta. We have not integrated yet with theta, just with r. So we have the integral from 0 to pi over 2. We plug in r to be 2 cosine square theta. So this is 2 times 2 cosine square theta to be squared minus here r, which is 2 cosine square theta, and that's raised to the 4th power. That's divided by 4. This is all times that sine theta d theta. To simplify that a little further, we have the integral from 0 to pi over 2. This gives us 2 to the squared is 4 times 2 is 8. Cosine to the 4th theta times that sine theta minus 2 to the 4th is 16 divided by 4 is 4. This is cosine second power raised to the 4th is to the 8th theta, and that's times sine theta d theta. Now we use a u. Oh, my space is running out. No problem. We'll fix it. Now we use a u du substitution. Let u equal to cosine theta. So du is negative sine theta d theta. So negative du is that lone sine theta d theta. Right? Took my sins and put them in a bag. Now let's see. What do we have? We have this is equal to. Let's write this as 2 integrals, if you will. So this is the integral negative 8. This is u to the 4th du. Negative du will represent, negative du represents that sine theta d theta. And it's going to be plus, because this negative and that negative would give you a plus 4 times the integral. This is from 0 to pi over 2, 0 to pi over 2. So over here we have cosine, which is u to the 8th power du. So now when we integrate, we get negative 8 times u to the 5th divided by 5. Just go ahead and just plug in u. U is cosine. Cosine to the 5th theta all over 5 plus 4 divided by 9 times u to the 9th, where u here is cosine to the 9th theta. And then this is evaluated from 0 to pi over 2. We do the evaluation at pi over 2. Cosine of pi over 2 is 0. So then it's minus this minus, so we get 8/5. Then minus 4 over 9th. We're evaluating the cosine at the 0, so it gives us 1. So we subtract 8/5 minus 4 over 9. This is 8 times 9, 72, and then 4 times 5 is 20. And so we have as our answer 52 over 45. So we were able to squeeze that in to that space pretty good. Now, if you notice, these two problems are in cylindrical coordinates. Cylindrical. What this is in spherical. Let's see. We integrate first with respect to rho. So we get a 1/3 rho to the third. So we just put the 1/3 here. The integral from 0 to 2 pi. The integral from 0 to power over 4. Then this is rho to the third. Here, evaluated from 0 to cosine phi. Then we have out here sine phi, d phi, d theta. So this is 1/3, the integral from 0 to 2 pi, the integral from 0 to power 4. And so rho evaluated at cosine phi is cosine cube phi times that sine phi there. You evaluate at 0, you just get 0. So this is now d phi, d theta. Jeez. Okay, better. So here we use a u-du substitution, very similar to what we did in the previous problem. Let u equal to cosine, du picks up negative sign. So just the same model. Cool if I could just take this guy and paste it here because it's the same setup. So if that be the case, this becomes a negative, the negative there, negative 1/3, the integral from 0 to 2 pi, the integral from 0 to power 4, and this is u to the 4th. Then du would pick up the sine, what here is phi, sine phi, d phi. Right? So out here we have d theta. And so we get negative 1/3 times the integral from 0 to 2 pi. We integrate that u, that gives us u to the 5th. How did that go from 3 to 4? It's getting late. This is u to the 3rd. So this is u to the 4th, all over 4. It's evaluated from 0 to power over 4, d theta. This is negative 1/12. Right, 3 times the 4. Integral from 0 to 2 pi. Oh, this was u. U is cosine. Cosine to the 4th. And this was phi. Oh, we got the 4 there for that 12. Mercy. Cosine to the 4th. Phi, that's evaluated from 0 to power 4, and then d theta. So we get negative 1/12, integral from 0 to 2 pi. We have the cosine at power over 4. I'm just going to go ahead and just write it. The cosine of power of 4 is 1 over the square root of 2, and that's raised to the 4th power. Then it's minus cosine of 0, and the cosine of 0 is 1. to the fourth power is still 1. D theta. So this is negative 1/12. This is just a number, so we pull that on the outside. This is 1 over the square root of 2 to the fourth power is 1 over 4 minus 1. The integral, to integrate d theta, we just get theta, that's evaluated from 0 to 2 pi. We simplify this. This is negative 1 over 12. Here 1/4 minus 4 over 4 is negative 3 over 4 times 2 pi, right? So the negatives cancel out. And so we get 6 pi up top divided by, just write it, 6 pi over 12 times 4. So this is pi over 2 times 4 is 8. Okay, so we're almost in the clear. Just 2 more problems. Now these problems, they want you to actually do the convert from rectangular coordinates to, it says here, cylindrical and spherical, and then evaluate the simplest one. So notice that x is bounded from negative 2 to 2. Y is bounded here from the negative square root of 4 minus x squared less than or equal to y less than or equal to the square root of 4 minus x squared. Right? And then the z is bounded below by x squared plus y squared, and then it's bounded above by the 4. Now we can look at this in the xy plane to see how it looks. So x goes from negative 2 to 2, and y is here, picks up when this is a form of a circle. This is below the y-axis, and this is the part of the circle above the y-axis. That's the negative 2 there. This is the complete circle. That means that the radius goes from 0 to 2 and theta goes from 0 to 2 pi. So 0 less than or equal to r less than or equal to 2, right? And then 0 less than or equal to theta less than or equal to 2 pi. What about z? Z goes from converting to cylindrical. This becomes r squared less than or equal to z less than or equal to 4. So this is the solid region, how it's bounded. So we write this integral. The x in cylindrical coordinates is r cosine theta. You have to put that r factor, remember, in there for cylindrical coordinates. And I'm going to do, see that theta is going from 0 to 2 pi? That's telling me that it's a complete circle. Something may come out with the energy to give us 0. So I'm going to calculate this first with d theta. dz and then dr. So we got theta going from 0 to 2 pi. Z going from r squared to 4. And then r is going from 0 to 2. So let's write this. This is the integral from 0 to 2. The integral from r squared to 4. It's the integral from 0 to 2 pi. This is r squared times cosine theta, d theta, dz, dr. Mercy Lord. Let's integrate with respect to theta. So we have the integral from 0 to 2, the integral from r squared to 4, and this is r squared. We integrate cosine, gives us sine theta. That's evaluated from 0 to 2 pi. And then we have dz dr. You integrate, you evaluate sine at 2 pi, that's 0. Then minus sine at 0 is 0. So this is 0. Well, 0 is 0. Right. Here, this evaluation gives us 0. Sine of, not power 2, sine of 2 pi minus sine of 0, right? The last one. The problem said convert to both cylindrical and spherical. I'm not. I'm going to do the easiest one. I'll tell you what, converting this guy to spherical, you can if you want to. It's hard. So I'm going to stop right there. Now for number 16, I will do both and show you both, but I will calculate the easiest one. So let's see. Here it's the x. X is bounded below and above by the 0 and the 3. Y is bounded below by 0 and above by this square root of 9 minus x squared. And then z is bounded below by 0 and above by this square root of 9 minus x squared minus y squared. So it's difficult to look in the third dimension by hand, so I will only look at what happens in the xy plane. So x goes from 0 to 3, and then y is the circle, it's the top part of the circle, but it doesn't go over to the second quadrant because x is bounded from 0 to 3. So it's this. So we have 0 less than or equal to, here r less than or equal to 3. And then theta is bounded from 0 to pi over 2, right? And then the radius is 3. So that's a good starting place for us. Now if we were converting to cylindrical, we have 0 less than or equal to z less than or equal to the square root of 9 minus r squared. So we want to convert this to cylindrical coordinates. So I have this triple integral, just write the integrals. This square root, that x squared plus y squared for cylindrical coordinates is r squared plus we maintain z for cylindrical coordinates. This is r dz dr d theta. So z goes from 0 to the square root of r minus 9 minus r squared. And then r goes from 0 to 3. And theta goes from 0 to pi over 2. Now let's look at, I will go by the instructions, let's look at converting this to spherical coordinates. So for spherical coordinates, we need rho, we need theta, we have theta, the bounds for that, and then we need the bounds for phi. Well, let's take that upper limit for z, and what you get there is that z is equal to the square root of 9 minus x squared minus y squared. Right? So that's the case. You square both sides, we get z squared is equal to 9 minus x squared minus y squared. And that gives us x squared plus y squared plus z squared is equal to 9. But x squared plus y squared plus z squared is rho squared equal to 9. So here we get rho is equal to 3. So we need that. We have also that r is equal to 3. We have theta is equal to pi over 2. So we got that from here. So we have rho, we have theta, we need phi. So to get phi, let's look at this. That sine phi, if we can go back and, without me having to redo the proof. Sine phi is equal to r over rho. Why am I using that? Because I have r and I have rho. Sine phi is r over rho, right? So we'll use that one. This is r over rho. R is 3 and rho is 3. Now I could have told you that the z-axis is above, is right on top of this guy, and it can't go no further than theta. So this is 1. So sine phi is equal to 1. When is sine equal to 1? When the angle is pi over 2. This implies that phi is equal to pi over 2. So it looks like we have everything that we need. So we're going to take this guy and we're going to convert him over here to spherical coordinates, and then I believe we can calculate that. It's a whole lot easier than calculating this. This is doable, by the way. A little algebra involved. I don't want to go there. I want to try to make this as simple as possible. See if I can write the spherical here. We have these 3 integrals. Here, this square root of x squared plus y squared plus z squared, isn't that equal to rho? So this is, right, rho is the square root of x squared plus y squared plus z squared. So this is rho. Then to convert to spherical coordinates, you've got to have the factor of rho squared sine phi anyway. And so this is d rho, d phi, d theta. It doesn't matter about the order, but whatever order you pick, the integral has to match up. So rho goes with from 0 to 3, I believe, 0 to 3. And the theta is bounded from 0 to pi over 2. And then phi is bounded the same way from 0 to pi over 2. So rho goes from 0 to 3. Theta, well, phi goes from 0 to pi over 2. And then theta goes from 0 to pi over 2. So let's write that downstairs over here. So we have the integral from 0 to pi over 2, the integral from 0 to pi over 2, the integral from 0 to 3. This is rho to the third times sine phi. This is d rho d phi d theta. And I think that's how I have that up here. Yes. So now we integrate. So we integrate with respect to rho. It gives us a 1/4. The integral from 0 to power over 2. The integral from 0 to power over 2. Here, this is rho to the 4th. Rho is evaluated from 0 to 3. This is sine phi d phi d theta. So we have 1/4 here times 3 to the 4th. Rho is evaluated at 3 times the integral from 0 to power over 2. The integral from 0 to power over 2. Sine phi d theta. So this gives us 81/4. It's the integral from 0 to power 2. We integrate sine, gives us negative cosine phi. That's evaluated from 0 to power over 2. This is d theta. So cosine at power over 2 is 0, then minus, this minus is positive, cosine at 0 is 1. So that just gives us 81/4 times the integral from 0 to power over 2 d theta. This gives us 81/4 theta. Theta is evaluated from 0 to power over 2. So we get 81/4 times power over 2. That gives us 81 pi all over 8. That's it. So everybody's happy, and I'm tired. Thank you. Have a good one.